Now then, I thought I'd knock something together for you after we had that chat yesterday, and probably the best place to start was calculation of floor joists, and I'll run you through this, and then if you've got any questions then let me know. But basically, I did it already on that other video relating to doing all of this via computer, but I'm going to run through it by hand, and then the computer stuff should make more sense. I certainly don't believe anybody should ever use a computer for anything unless they could actually do it by hand if the computer broke down. That's the only way you can ever guarantee that you don't have, well, you can never guarantee garbage in, garbage out. But if you know what you're doing by hand, then the computer will only speed things up, because these computers can produce dangerous structures with a minimum amount of effort. Okay, so here we go. Like any the papers that you've got on the AutoCAD file that you've got now has 3 or 4 sheets before this, but I can talk through them. We'll start at the point where we establishing the span of a floor joist between 2 given points, in this case between a beam and the external wall. The clear span there is 4,100 millimeters, and first thing we've got to do is ascertain the load. Now there's the load. I've identified it as 2 parts of the load. The first part of the load is, in old money, is dead load. In super beam money, it's dead load. In the British standards, it's dead load. In the European standards and Eurobeam, it's permanent action. But the first thing you've got to do is to figure out what the load of the floor is. The dead load, permanent action of the floors may vary, but it's always going to follow this particular line, where we've got the floor decking, 22 millimeter chipboard, maybe 18, and I've got that at 14 kilograms a square meter. The floor joists, you can work out, the weight of the floor joists. They'll be quite heavy floor joists. They'll probably be set by about 8x2s. And it's going to be close. It's going to be around about that for this. Bit of insulation for sound. Plasterboard and skim, just a normal half-hour floor within a domestic building. Obviously, there can be 2 or 3 layers of plasterboard depending upon sound insulation requirements, etc. And they'll multiply up accordingly. But this generally comes in at around about 50 kilograms a square meter for a normal floor construction. And to convert kilograms into kilonewtons, we multiply by acceleration due to gravity, which is 9.81. So multiply that by 9.51 by 9.81, divide by 1,000 gives kilonewtons. I know this unit malarkey is tough to get your head around at times, but that effectively gives 0.5 of a kilonewton per square meter. The imposed action, i.e. the variable action, i.e. the load of people walking around on the floor, or the missus's shoe cupboard that's full up to the brim with shoes and clothes and wardrobes and chairs and tables, that all comes into this load, which has been established for domestic at 1.5 kilonewtons a square meter, and that's roughly, well, it's not roughly, it's 150 kilograms a square meter. So it's a couple of guys my size stood per square meter, and that's what the allowance is for the floor. That's what you've got to take into account on the calculations. So therefore, dead plus imposed, or permanent plus variable, is going to be 2 kilonewtons a square meter, and that you'll see that in a million calculations if you see it once. Floor, 2 kilonewtons a square meter, and it's generally for a half-hour floor. If it's got a couple of layers of plasterboard, or the chipboard or the decking is denser, then it'll go up slightly, but it's going to be hovering around that particular area. Oh, I want to pan, don't I? Okay, so I then talk about the conversion, the 9.81 multiplied and divided by 1,000, and why that's the case. And that's 1.5 kilonewton a square metre variable action imposed load. There's a few other examples of it. Ceiling load, as we assume 0.5 of a kilonewton per square metres for all the crap you've got in the loft, generally far too low, to be fair. And a 0.9 kilonewton point load, one or the other. And well, no, both together as it happens, I think. But it used to be 0.75, but obesity's kicked in, and now it's supposed to represent a man. So, like I said, obesity's kicked in. It used to be 0.75, and now it's 0.9. Snow load's about 0.6, depending upon a few factors, and like I said, domestic floor loads at 1.5. Okay, so now we've got to figure out how much of that loading pertains to the floor joist or has been applied to the floor joist, and it's no more difficult than multiplying it by the centres. So if the centres is 0.4, and always as a go back aside, because this is a one take video, to go back one step, always identify the loads as separate. So the dead load and the imposed load, or the permanent action, the variable action, depending upon what code, because that's the way things are now. It used, when I first started doing this malarkey, we used everything was lumped together, because the codes never identified them as being separate. So we used to lump the dead loads and the imposed loads together, but now keep them separate. So if you can remember that the permanent action of the floor, the dead load of the floor, was 0.5 of a kilonewton a square metre, which was 50 kilograms a square metre, and we multiply that up by the floor centres in metres, and that gives you 0.2 of a kilonewton per metre of the floor joist. So for every metre of the floor joist, 0.2 of a kilonewton is being applied to it. And the same thing goes for the imposed or variable action. That was established at 1.5 kilonewtons a square metre. And again, you just multiply it up, because that's how much of the floor is being taken by the floor joist. And that works out at 0.6 of a kilonewton per kilonewton per metre run of the floor joist. That's quite important when we come to work out the bending of the floor joist. So that gives a total of dead plus imposed of 0.8. And again, in the old days, that's what we used to use. I'm going to have a swig of my tea. That's what we used to use. We just use 0.8, used to lump them together. You don't tend to do that these days because of the way that the Eurocodes and the more later British standards apply. But we don't really need to get into that too much. Super beam can either use combined dead and imposed loads, or you can input them. Individually. But we're not going to go down the computerized route. This is going to go more down the manual route. So the first thing we do, we draw a little diagram, and there's a little diagram, a little beam diagram. And first thing we do, we increase the clear span by 100 millimeters, and that gives the effective span. And we can get into that at a later date, but basically you always add 100 millimeters onto your floor joist, your clear span of your floor joist. And there's the load over the top. In this case, I put the total load of 0.8, but really it should have had either dead or permanent action of 0.2, or imposed or variable action at 0.6. Right, don't have to worry about that too much. And I kind of keep homing in on super beam and stuff like that, because I think that's how everybody does this. But this is basically, if you put the information in, this is the information you're going to get out. In this case, we've got 4.2, and we multiply that up by 0.8. That will give the total load on the beam, because remember that 0.8, which is the combined dead and imposed load, and if we multiply 0.8 up times 4.2, 0.8 times 4.2, we get 3.36. Write that down, because I haven't got I have got the facility to write down on AutoCAD, but it's going to be a chew on. As you well know, you've got a third Dan in black belt, and I've only got a third Dan in AutoCAD, and I've only got a black belt in it. So that gives 1.68. That's the load either side. The load either side of that's being supported by the which is the load acting upon the supports, I should say. So that's the load that will be acting on your floor, on your joist hanger, or the floor, or the load that may be being supported by the beam, or the load that may be supported by the wall. Okay, so that's basically what that is. From the effective, because I'm doing this off the top of my head. So the equation for the bending moment, like I said to you, bending's very simple to figure out. You apply a load to a beam and it will bend. Depending upon how stiff the beam is, will depend upon how much it bends. We talked a little bit about stiffness the other day. So if you apply a load to a 4x2 in the strong axis, it will bend. But if you apply that load to the weak axis, you spin that joist round through 90 degrees, and it will bend even more. And we talked about the section properties and stuff like that. But for when there's a uniformly distributed load along this beam, which there is, because that's a uniformly distributed, because it's kilonewtons per meter run, and it's the same load all the way along the beam. Now, if it's the same load all the way along the beam, then you can use an equation called the bending equation, which is WL/8. Or that W would be the total load, but because we're using the UDL load, we'll use WL²/8, right? So in this particular case, W is 0.8, the span L 4.2 times L 4.2, we divide that by 8, and then we get a bending moment of 1.76 kilonewton meters. Now the bending moment the units for bending moment is kilonewtons per meter, and you can almost imagine that as well. It can, if you have a scaffold bar and you're trying to apply some leverage, then how long the bar is and how much force you put in that bar to apply the leverage will ascertain how much load you can actually move. And that's the torque is measured in the same units. It's just a force times a distance, and force times distance will give you a bending moment. Okay, so that's basically how that kind of comes together. So we've got like I said, the reaction of the beam, how much of the joist, how much load is being applied to the hanger, to the beam, to the wall, That's this fella here, 1.68 kilonewtons, which is 168 kilograms. Now, again, what we're talking about, the BD squared over 6. Using this method, we need to have a trial section, i.e. have a stab. So you think, oh, let's try, it's 4.2 meters. Let's see if we can squeeze in a 200 per 50. So you've got to figure out what that is in terms of shape, the strength of the shape of the member, and that's what this section modulus does. And the formula is BD squared over 6. So if we try in a 200 millimeter beam, 200 millimeter joist is 200, which is D, the depth, times 200, which is the depth, the D squared, remember, times 50, which is the B, the breadth, divide by 6. And that gives that number there, 333,333 millimeters cubed. This is what I was saying the other day about units. Units can get a little bit out of hand, but when you start using them a few times, it kind of all clips into place. Another swig of my missus's tea. Right, now the bending stress in the beam is very easily calculated by dividing the bending moment, which we figured out, on WL over 8, or WL squared over 8, and dividing that by the section modulus. That kind of makes sense, because the bending moment, we have a bending moment, and the stress in that beam will depend upon the shape of the beam. So if the beam is extremely deep and extremely big, then the stress is going to be extremely small. If the beam shape of the beam is extremely small, then the stress is going to be extremely big. So if you want a small beam, you need a strong material. But we're working with timber here, so we're working at a stress between 5 and 10 newtons per millimeter squared. But with steel, you're working at around about 170, 200 newtons per millimeter squared. So this kind of makes sense. So what we do, we're dividing the shape of the beam by the amount of bending in the beam, and that will give us a strength. That'll give us a stress. And in this particular case, we're playing with units here. That 176, you need to multiply that by 1,000,000, which is 10 to the 6. And we've already got, that turns that into newtons. We've already, Newton millimeters. We've already got our section modulus in millimeter, in a variation of millimeters, and that will give the stress. And in this case, the stress on this particular situation is going to work out, if you work it out and you calculate it, at 5.04 newtons per millimeter squared. Now, the basic permissible stress for C16 timber is 5.3, so our 5.04 is okay. And the basic permissible stress for C24 timber is 7.3. Now, you can multiply them up by 1.1 if it's a joist, or if it's a rafter, if it's a ceiling joist, where 4 members or more share a common load, like joists, rafters, multiple beams. Permissible stress can be multiplied up by 1.1. And the idea of that is that if you have, the more pieces of timber that you have sharing a common load, the less chance you will have of having one of those pieces of timber being useless, i.e. knots, veiny edge, all of the kind of things that will reduce the stress of the timber. And because timber is natural, you can't guarantee it. There's no quality assurance systems for growing timber. There is for selecting it, but obviously things get through, and these little statistical factors are there to increase the stress where the statistics would say that there's less chance of a poor piece of timber making it into the structural member. So you can because this is a floor joist, you can multiply these stresses up by 1.1. I'm going to go back to that and that more or less is it as far as stress is concerned. So as far as stress is concerned, and like I said about stress is we're working out the stress at the extreme of the member. If you bend a beam, the top part of if you apply a load to the top of the beam, like you do in a floor joist, then the top half of the beam will be in compression and the bottom half of the beam will be in tension. So what would generally happen in a timber beam, if you apply excessive load, it would start splitting at the bottom as the extreme fibers of timber at the bottom of the beam started to fail because the stress was too high. So that's basically what these numbers, or that number, is ascertaining. It's ascertaining that the compression at the top of the beam is at the extreme of the beam, the top, is 5.04 newtons per millimeter squared, and at the bottom of the beam the tension is 5.04 newtons per millimeter squared, and those two, and basically those two, it's within these two numbers here. So you could use C16 or C24 in terms of stress. That's stress out of the way. The problem is with timber, and well, with most materials, to be fair, is that deflection becomes the criteria of design when the span starts increasing. So around about 3 meters, and timber will be determined more on deflection than it is on stress, unless of course you don't care, or it's not critical whether the beam deflects or not. So this is a calculation for deflection, and it looks a little bit excessive, but with calculators and spreadsheets and stuff like that, it's very, very quick to ascertain. The 5/384 is a constant. That's because it's a uniformly distributed load. If it was a point load, that would change. That becomes 1/48. But because it's a uniformly distributed load, it's 5. So what we're left with is W, small w, which is the uniform distributed load, which in our case is 0.8. The combined is 0.8 of a kilonewton a meter. And you multiply that up by the length of the effective length to the 4th power. So L times L times L times L. And then you multiply that up by 10 to the 12. Right, so that's 10 with 12. That's effectively 1 with 12 noughts after it. And then you divide that by the obviously, forget about that 5. You divide that by E and I. And we talked about E and I. The only thing that determines the stiffness of any structural member is the material it's made out of and the shape of the material. Now, the E is the strength of the material, for want of a better word. And timbers, as you can see here, it's between, in this particular case, but it's generally between 5 and 10,000 is 10,000 newtons per millimeter squared. That's generally the range of timber, depending upon its grading. And the I is a derivative of Z. In this particular case, it's BD cubed over 12. That determines the shape. This is that one, and that's for a rectangular beam. That I identifies the shape. So if the material is extremely strong, and the shape of the beam is conducive to stiffness, i.e. deep rather than wide, then you're going to end up with a stiff beam, which you can apply a lot of load on it before it starts to deflect. So that's the variables for deflection, which is intuitive really. It's going to depend upon the load. It's going to depend upon the length of the beam. Longer the beam is with the applied load, is going to deflect more. It's going to depend upon the material of the beam, and it's going to depend upon the shape of the beam. How hard is that? So all of that maths just intuitively explains what's going to happen in reality. A lot of load, a weak beam, a weak small beam, lots of deflection, because this number is going to be higher than that number. But if the beam is extremely, if the beam is made out of a strong material, and the I and that I is considerable, then this part of the number is going to be bigger than that in relative terms, and you're going to end up with a small deflection. So that's basically what I've explained there. And I kind of touched on this before, that if you've got one member acting together, how can one member act together? I'm not even going to edit this out. One beam acting alone, there's a possibility that that piece of timber is not particularly good. So you have a low E value. Remember, E is the strength of the material. And you stick two of them together, and there's a good chance that at least one of them's decent or better, and you can start increasing the E. You put three of them together, and you can say, oh, right, well, there's a good chance that at least two of them is going to be okay, and so on and so forth, until you get up to E mean, which is when lots of members are acting together, floor joists and stuff. So you can use E mean. That's for C16. Same thing applies to C24. And this is all down to the fact that timber is a natural material, and all of these numbers have been figured out through statistics. Okay, so let's crack on and do a bit. What does that say? Blah, blah, blah. I think I've more or less explained that. Right, so let's have a look at, let's run through the calculations. Again, straight calculator thing. So I, in this case, for deflection, so we use Z for stress and we use I for deflection. Z is derived from I. Z is I over Y, and I kind of touched on what Y was. It's the distance. It's distance from the neutral axis to the point where you're going to try and ascertain what the stress is. Not really of much importance is Y in normal structures, because you're only ever concerned about what the stress is at the extreme fibres, the top and the bottom of the beam. There's certain situations where it applies, but it's black belt structures, not really necessary to understand what's going on. So in this case, it's B, which is 50, D cubed, which is 200 times 200 times 200 times 200, divided by 12, and you get this big number, 33.3 times 10 to the 6. And that's millimeters to the fourth. Remember, it was millimeters to the third. Units is the biggest problem in structures, I think. Structures themselves work themselves out. You can intuitively figure out what the hell's going on. but the units can be all over the shop. So let's run this through that what appeared to be a difficult calculation, but it's not a difficult calculation. All the variables that you need to ascertain how much this beam is going to bend in terms of distance rather than stress, which we've already calculated, is there. We need to know the load. The load's going to determine how much it's going to deflect. The span's certainly going to dictate how much it's going to deflect. Hence, that's why it's to the power 4. E, how strong the material is you're using, and I, the shape of it. Because if we, that other exercise we went through, if we made the 200 by 50 flat, it would be 50 times 50 times 50 times 50 times 200 divided by 12. That number would be substantially less than 333.3 times 10 to the 6. So that I is critical, and as explained. So all of these numbers here just represents what we already know, which is common sense. That's the constant, which you don't have to worry about. But there's the load, 0.8, which is 0.6 imposed load or variable load, and 0.2 dead load or permanent action, multiplied by the span, which is the effective span, which is the clear span plus 0.1, and that is multiplied by each other 4 times. So 4.2 times 4.2 times 4.2 times 4.2. That fella there just converts all of these meters into millimeters, and then you divide it by the 384. The E for floor joists, lots of them acting together, so we can use the E mean, multiplied by this number here, and then you just work it out, and it works out at 9 millimeters. 9 millimeters is your deflection, and the acceptable is 0.03 of the span, which is 12.6. So the joist is okay. So that's an example of running through it manually rather than running it through on a computer. I don't know what else is on this. No, it's just exercises on this screen. So hopefully that makes complete sense. And like I said, it's all intuitive. It's just a matter of making sure that the numbers match that intuitiveness, for want of a better word. Okay, that's it. Catch you later.